So we are working on moving different functions around and seeing how we change the equation and then look at how that graph responds when we change the equation. And so one way that you got to get used to is starting with what's called a parent graph. And that is sort of the basic shape that we're going to be working with. So you can use anything as a parent graph. In this one, let's just do x squared as our parent graph. And then what we'll look at is a new function that's defined in terms of the old function. So let's see if Desmos will do what I want it to do. So I'm going to define a new function called g of x, and I'm going to say it's what f of x was plus 1. I just want you to notice what happened when I did plus 1 to the graph. So notice what direction the graph moved in. Notice if it went up, down, left, or right. Notice how far it went, and try to think about what did I type in to the equation that made the graph move that way. So I have plus 1 looks like that. Let's try plus 3. Let's try minus 3. At this point, hopefully you're seeing some sort of a pattern that the plus moves the graph up, the minus moves the graph down. And you can summarize that. A lot of times I'll use the letter K for what I'm adding or subtracting on the outside. And if you type in the letter K, it allows you to put this little slider right here. So you can keep your eyes right here on what the K value equals. And then I can play with the slider. You see that as K gets bigger, my blue graph goes up. As K gets smaller, my blue graph goes down. My blue graph is equal to my red graph where? Right when K equals 0. That's when they're equal to each other. So to summarize what I'm seeing here, vertical movement called translation. Vertical translation is pretty simple. Vertical translation just means you're adding a value on the outside of the function, and that moves your function up or down. One thing that's kind of cool is I mentioned that this works for any parent function. I happen to choose x squared because it has a nice shape. I can change f of x to just x, and we can play the same game, how the blue line is just slid up or down k steps from the red line. I could change the red function, the parent function, to absolute value of x. Now you have this cool V shape. And again, the blue V is just k steps vertically translated from the red V. Okay? Just to show you one other funky looking thing that we're going to look at this year. Sine of x, this wave function, you can see that the blue wave is parallel to the red wave. It is just translated vertically by k steps. Okay? So vertical translation just means plus or minus at the end of the function. And that makes sense because the y values are what you get out when you plug in an x value. So I could do this here. I could actually make a table. Let's see. If I hit this, I could make a table here and make the y value equal sine of x. Will it do that for me? Oh, never mind. Does that work? Never mind, it doesn't work. Lied. There's a way to do it. If I make y equals sine of x and then there we go. I can make the value into a table, right? And what I want you to notice is that if I add something at the end of it, like plus 3, and make that into a table, what you'll notice is that the table on the bottom is the original sine of x, and the table on top is the sine of x plus 3. And you can see that all the y values are just 3 steps bigger than the old y values. Okay? But what I'm going to talk about next is what about moving things side to side? So what I just said is when you add or subtract outside the parentheses, it changes the output. It changes the y value. What we're going to do next is try to slide it left or right. And by now you should be thinking, okay, if adding or subtracting on the outside moves it, outside moves the output, moves it up or down, then maybe adding or subtracting on the inside will move the input, will move left or right. If that was your hypothesis, you're correct. Let's do adding 1 first. Okay. Notice that when I added 1, the blue graph is at the same height as the red graph. It is just shifted left by 1 step. If I add 3, the blue graph is shifted 3 steps to the left of the red graph. If I subtract 2, the blue graph is shifted 2 steps to the right. Sine of x is a little hard because it repeats itself, so shifting it to the left is actually equivalent to a shift from the right because it's going to line up on itself anyway. So let's change the parent graph to something that's easier to look at, like absolute value of x. Notice that when I have x minus 2, my blue graph is 2 steps to the right. When I have x plus 2, my blue graph is 2 steps to the left of the red graph. And that is probably opposite of what you would expect. If I just asked you to predict what direction does your graph go when I do x minus 5, many of you would think, well, x minus 5 is over here on the left, so my graph's going to go to the left. But notice that my graph actually goes 5 steps to the right. So one connection that a student made that I thought was really nice is thinking back to when we did polynomials. So when we did polynomials, we looked at things that looked like this: x plus 3 times x minus 2 times x minus 5 squared, blah, blah, blah. What I want you to notice is that every time it hit the x-axis, the number was the opposite direction of what you might expect. When I see x plus 3 in my equation, it actually hits the graph at negative 3. When I see x minus 2, it hits it at positive 2. It's a very similar idea here that when I type in x minus 5, it actually moves it to a positive 5 on the x-axis, as opposed to moving it to the left like you might expect. Another way to see this relation is to turn these into tables. So here's the original x and y values. Here are the new x and y values. What I want you to notice is that I'm going to scoot this table down a little bit. What I want you to notice is that, there you go. It takes, let's start here at this first point on the red graph. This first point is negative 2, comma 2. It takes me all the way until x equals positive 3 on the blue graph to match up with the red graph. Why does that work here? What we're trying to do is we're trying to get from the blue graph back to the red graph. So we're saying the g of x equation is actually f of x minus 5, because when we plug in an x value here, we're plugging it in on our new blue graph right there. Okay? So if I plug in, for example, 3, what I'm doing is I'm doing 3 minus 5 and looking it up in my old graph. And so g of 3 is going to be the same as f of negative 2, right? For example, g of 3 is the same as f of 3 minus 5, which means g of 3 is f of negative 2, and the 3 is 5 steps to the right of negative 2. And so what that means is that g of x is translated 5 steps to the right. Okay? Because what we're looking at is we're looking at the new graph as compared to the old graph. One way to write this is to realize that my new x is equal to my old x minus 5. And so if you add 5 to both sides, you get that your new x plus 5. No, that's backwards. Ha. Just like I was saying, it's very easy to get this backwards. So that when you look at the old x values, that you have to add 5 to it to get to the new x value. That it takes my red graph plus 5 to land on my blue graph. So it's really simple, I think, with the vertical. It goes the way you would expect it. Plus goes up, minus goes down. It goes backwards of the way you would expect it with the horizontal. I think the easiest way to keep it straight is to choose a particular point, like choosing this point right here that corresponds to this point here, and realizing what direction your graph moved, or choosing the lowest point here and the lowest point there. So we'll keep working on it. Please let me know if you got any questions or comments, and I'll try to help out.